Hello everyone, welcome to my videos. This is the very first video on the topic of fundamental differential equations. Normally, this is covered as a sophomore level course at the university. We will start with the very first chapter, which is an introduction to the whole topic. Okay, so let's begin with a definition. It's a very loose definition of a differential equation. So it's literally an equation which contains the derivatives of the unknown. And usually such equation comes as a consequence of a mathematical model for some physical phenomenon. Through the sequence of these videos, I intend to cover two classes of differential equations. The first one is called ordinary differential equations, where only ordinary derivatives of the unknown will appear in the equation. And the second class is partial differential equations, where the unknown depends on multiple variables and the partial derivatives would appear in the equation. So this one, we call it ODE for ordinary differential equation. And this one we will say PDE for partial differential equation. Personally, I work in the field of nonlinear PDEs. Therefore, I am quite sensitive to the acronym PDE. And one day, I found out that PDE also stands for Pennsylvania Department of Education. That information made me feel quite unstable. Okay, let's cover some concepts related to differential equations. And the first, system. What do we mean when we say a system? A system means that you have more than one equations and you have more than one unknowns. So it's a collection of several equations with several unknowns. The second concept is the order of the equation. The order is determined by the highest order of derivatives. This could be ordinary derivatives for an ODE and partial derivatives for an PDE. And the third concept, probably is the most important one here, is to decide if an equation is linear or nonlinear. Okay, so let's just spell it out to make it simple. Let's say y is your unknown. Then, if your equation can be written in this form, let's take a close look what it is. So it includes y to certain derivatives, nth derivative, n minus 1th derivative to y without any derivative. And what is multiplied with these y or y derivative terms is something that does not depend on y. So we call this A0, A1, all the way to ANT. And it could equal to some function here that does not depend on y. If you can write your equation into this form, then it's a linear equation. And if you cannot do that, then the equation is nonlinear. So two things really to master here that we should feel very comfortable with. That is to identify the linearity and the order of a differential equation. Okay, we'll take some examples. Okay, let's look at this first example. Now, y is the unknown, and we have 4 examples. And the question asks you to identify the order and the linearity of the equations. Okay, so let's intend to put the answer after these equations. So we'll put order here, and we'll put the answer to if it's linear or not below here. Okay, let's look at the first equation. Let's identify the order. So remember, the order of the equation is the highest derivative. So here there's only one term that involves a derivative, and that is y prime. So that's first derivative. So the order is 1. Okay, so is this a linear equation? How do we find that out? Well, we see that all the terms involving y or y prime shall be multiplied by terms that does not involve y. So can this be linear? Let's look at the term that's multiplying to y prime, a term here. Does it involve y? Yes, it involves y. So this cannot be linear. So no. Okay, so let's move on to the second equation. What is the order of this equation? So we look at the derivative terms, and we find out that this one contains the highest order of derivative, which is the second derivative. So the order is 2. Is this linear? Let's check every term. Look at the first term. Y prime is multiplied by 3, which does not depend on y. And then y is multiplied by t plus 4, which doesn't depend on y. T squared is just t, it doesn't have y in it. And then y second derivative is multiplied by 1 and doesn't depend on y. Okay, so all the terms pass the test, so this is a linear equation. And let's look at the third one. Okay, the order, probably you see it right away. Third derivative is the highest, so the order is 3. Is this linear? Let's look at each term. This term contains just y. Third derivative multiplied by 1, that's okay. What about this term here? I have cosine 2ty, and this is not in the form of y multiplied by something that doesn't depend on y, because 2ty is inside a cosine function, a nonlinear function. Okay, so it's not linear. Okay, so what about the last example here? The order is determined here, the third derivative, the order is 3. Is this linear? Let's check each term. This term is okay, it's linear. This term also is okay, it's multiplied by square root of t, doesn't depend on y. And this is cosine t, which is okay. What about this term? E to the y. This is not y times a function that's not depending on y. So this term here makes the whole thing nonlinear. Okay? So I hope through these examples, the two concepts shall be clear to us now. Now the next concept is the concept of a solution. So what is a solution to a differential equation? It is a function that satisfies the equation. So we have several things here. It has to satisfy the equation and the boundary condition and the initial condition, if any of these are given. Okay? And we also require the derivatives shall exist. We can practice our understanding of that through some examples. At least by this definition, we can verify that a given function is a solution. Okay? So we want to verify here this function, the exponential function, y is e to the at, to show that it's a solution of the, this is another acronym, initial value problem, IVP. That is a differential equation y prime equals a y together with an initial condition given y at 0 equals 1. Okay, so this initial condition simply means when t equals 0, y equals 1. Okay, so to solve this problem, we need to check if it satisfies the equation and the initial condition. Let's go through that. So the equation says y prime is a times y, and y is e to the at. So plug that in, e to the at. If you differentiate y prime e to the at, what you get is, and the exponential function keeps the exponential function, and then you get an a in front. So it's a times e to the at. And then here you recognize e to the at is just y. So this is a times y. So we see this function satisfied the equation. Okay, now let's look at the initial condition. Y at 0. When t is 0, what is the y value? So you set t to be 0 here, then you have e to the 0, which is 1, which is the initial condition. Okay, so they are both satisfied. Then we conclude that this is a solution to the initial value problem. Okay, let's take another example. So here we want to verify that yt equals 10 minus c times e to the power negative t, with the c here an arbitrary constant, is a solution to this differential equation, and we don't have any initial value given here. Okay, so all we need to do is to see if this satisfies the equation. Okay, so in the equation we see that we have y prime. Let's compute the y prime where y is given here. So if you differentiate this, what you get is this term here differentiated in t, which just picks up another negative sign. So it's c times et. So once you have y prime and y, now you can plug into the left-hand side of the equation. So y prime plus y would equal to this guy, c e to the negative t, plus this. This is the y, remember here? And then we see that the two exponential terms exactly cancel each other. Then we just have 10. So we verified that this is a solution for any constant c. In the next example, we will try to solve an equation. The equation is this: t plus 1 times y prime equals t squared. I know we have not talked about any solution algorithms and strategies, and yet for this example we shall be able to solve it just using basic calculus. Okay, let's manipulate a little bit. So we wish to move this term to the right hand side of the equation. That is, we'll divide both sides by t plus 1. We can do this provided that t is not negative 1, so that this is not 0. If we do that, then we see y prime equals t squared over t plus 1, which is a function depending only on t and not on y. Okay, so from here you might be thinking, I think I can solve this. If I know the derivative of a function, how to recover a function is by integration. I can integrate this in t and get the y here. Okay, so keep that in mind. Then that motivates us to manipulate the expression on the right hand side here into something that is easy to integrate. Okay, let's go through some manipulation. So what I did here is I subtracted 1 and add 1. So I add 0, which is nothing. And then I factorize t squared minus 1 into t plus 1 times t minus 1, 2 terms, and then plus 1. And why did I do that? Well, because we see that now the first term here, I will have t plus 1 cancels t plus 1, which remains only t minus 1, this one. And then the 1 here will stay on top of t plus 1. So I have now 3 terms, t minus 1 and 1 over t minus 1, and all of them is easy to integrate. Okay, now let's integrate. So y equals the integral of y derivative, and let's plug in the derivative here, and then let's find out the antiderivative of each term. So for the term t here, we get t squared over 2, and for the term negative 1, we get negative t. And for the term 1 over t plus 1, we'll get natural log of absolute value of t plus 1. And don't forget, there is an arbitrary constant called the integration constant that we should add to the solution. Okay, so the adding of this arbitrary constant tells us that for a differential equation like this, if you do not specify some initial condition, and there could be infinitely many solutions, because you can pick C to be anything, and this is a solution. And if, in the case, we shall specify some initial condition, then you can actually determine the value of this constant. Let's see on the next slide. Okay, now we add additional condition. Initial condition, like y of 0 is 1. This means when t is 0, y is 1. Okay, so we plug t is equal 0 and y equal 1 in the equation form. So y of 0, that will be 0 plus ln of 1 plus c, which is just c, and that must be 1. So this allows us to nail down the constant c is 1. And now you have your solution with the initial condition, that is here where you put c to be 1. So now this is not a multiple function, it's just one single function here. Okay, let's do a quick summary. For equations of the form y prime equal a function of t, we call it f of t, we can solve it by integration. So y will just equal to the integral of f of t. And this is an indefinite integral, which would include an arbitrary integration constant. And if, in addition, an initial condition shall be given, then we can use it to determine the integration constant. Now let's review some common integrals that we have learned in our calculus course. Just a quick review. These are the most common ones, and we'll be using them repeatedly. Okay, so the integral of polynomials x to the power n is 1 over n plus 1 x to the power n plus 1 plus a constant. This holds for n not equal to negative 1. If n is negative 1, then that's the integral of 1 over x. And that's the natural log of absolute value of x. Okay. Another class are the trig functions. So the integral of sine is negative cosine plus constant. And the integral of cosine is sine plus constant. And the integral of the exponential function is the exponential function plus a constant, and the integral of a to the x is a to the x over natural log of a, and of course plus a constant. Integration by parts, which is also very useful for these differential equation topics. Okay, so integral of u dv is u times v minus integral of v dv. And for u and v functions of x, we can write it out even as a definite integral from a to b. U x v prime dx is equal to u times v, evaluated at the a and b interval end, minus integral of vx times u prime dx. So the derivative is moved from v to u. Okay. Finally, let's review the chain rule. It's for composite functions. If you have a function f that depends on g, and g is a function of t, and then you differentiate this function in t, what you have is f prime of g evaluated at t times g prime evaluated at t. Okay, so all these, we should have them on our fingertips, and we will use them over and over to solve differential equations. Hope you enjoyed this video. I'll see you next time.